a motivation to consider what is called a non-uniform model of computation. Can we have algorithms or ways to decide different size instances differently, right? And circuits are a computation model where we can do the non-uniform computation, right? So, in other words, can we have different algorithms for different problem sizes, right? And this is one motivation, and this is this because of this reason, right? People have studied. This was one motivation to study the circuit complexity model rather than the Turing machine model, because in a way to resolve P versus NP, people thought that because of this peculiar property, maybe circuits are the way to go, and people tried various approaches using the circuit computation model. However, it was later shown that it is unlikely that even this question is going to be true. The same question that Karp and Lipton have asked here, it was shown that this is unlikely to be true, right? Because if this was true, something else unlikely happens, right? However, this was a initial motivation to study circuits. Perhaps this was the way to go, and this distinction may help us resolve P versus NP, right? And Turing machine, even though we started with Turing machine in this course, and we consider it equivalent to our everyday computers that we see. However, it's still a rather complicated model. So you have a tape that runs around, you have this tape that reads and then moves right or left and then erases, rewrites, right? So this is a rather involved, intricate model. Whereas, as you will see, circuits are very, very simple, straightforward model, right? So perhaps it may be easier to study a simpler model. Perhaps this may lead to an easier resolution for P versus NP. This was another hope, right? And until now, lots of people have worked on P versus NP using the circuits, but still there has not been much success, right? Another reason for studying the circuit complexity model is the fact that this captures the notion of parallelism in a nice manner, and that is one reason why this may be good to understand. So this is a third reason why circuit computation model has been studied, right? So these are the motivations, and we'll first start, as I said, with just one language, and we will see different ways to realize that language, right? So this is what we'll start with. Okay, and that will give you an idea of what circuits are before going to the formal definition, right? And I'll just briefly describe what they are so that you have some context, and we'll formally define it in the later lectures. So circuits are directed acyclic graphs. So they have direction, they have graph without cycles, where you will have many inputs, let's say n inputs, and a single output. So in the directed acyclic graphs, there will be sources and sinks. Sources are vertices that do not have incoming edges, and sinks are vertices that do not have outgoing edges. So in this we have n sources and one sink, and all the non-source vertices are a logic gate like AND or NOT, right? So we'll use this symbol to denote AND, and this symbol, the V symbol, to denote OR, and this symbol to denote NOT, right? And what I'm going to describe is one language and different ways to realize that language using the circuits, right? And in fact, this lecture is most of this material for this particular lecture and the next lecture, where I think I'll move on to, is from if you search online for IARCs and computational complexity theory by Professor V. Vinay, right? If you Google for IARCs, computational complexity theory, and V. Vinay, IR stands for Indian Association for Research in Computer Science. It's an old association. There is a bunch of lecture notes that you will get by Professor V. Vinay, and this is the first lecture of that course, right? So that's one reason it's a very nice example to illustrate the circuit complexity model. So again, you'll find the same things, but anyway, I will also provide you with these notes. Okay. Right. So what is the language that we are going to consider? The language that we are going to consider, in fact, it's a family of languages called TH N subscript N superscript K. So TH stands for threshold. So this is the set of all n bit strings, n bit 0, 1 and n bit strings that have at least k ones. So this is a set of all n bit strings that have at least k ones. So just to understand this, we will see some simple examples. When k is 1, this is the set of all n bit strings that have at least 1 1, right? In other words, it's just the OR function. And when basically at least one of the x1, x2, x3, up to xn has to be, at least one of them has to be 1. So this will be 1 if this will be in the language. So if at least one of them is a 1. Threshold nn means that of the n bits, there has to be at least n of them have to be 1s, which means all of them have to be 1s, which means it is the AND function, right? All of them have to be 1s. And next is when k is n by 2, right? So half the bits have to be 1s. In other words, it's what is called the majority function. So at least half the input bits have to be 1s. So when n is odd, this is the actual majority. When n is even, it's kind of like the majority, right? Half of them have to be 1s, right? So this is sometimes called the majority function. And what we will see is from this threshold family, we will see the language threshold n with k equal to 2. Okay, so x1, x2 up to xn are the individual bits, right? These are the individual bits, and the strings in the language are those strings that have at least 2 1s. Okay, set of all x that have at least 2 1s. Okay. And maybe you may want to ask, how would the Turing machine compute this, right? So you could just write a simple Turing machine algorithm that just scans the input from right to left and just looks for 2 1s, and once it sees 2 1s, it can just stop. Right? So this, it just needs so all it needs to remember is whether it has seen at least 1 1, right? So that it can be just 1 bit flag. And of course, it also needs to, it doesn't even need a counter, right? It can just go 1 1 1, like one step, one cell to the right till it hits the end of the string. It doesn't even need a counter. So all that it requires is order n time. So if you have a Turing machine, there is a order n time. This is an n. Sorry if you are not able to read my handwriting. Order n time and constant space algorithm. Right, this is a standard thing. Anyway, what we are going to see today is not Turing machines but circuits. And we will see, again, as I said before, we will see circuits using for threshold n 2, threshold 2, using AND, OR and NOT gates. Okay, so this OR is written like a V, AND is written like a wedge. It's called a wedge, but it kind of looks like an A without the horizontal bar, and NOT as this. Right. And some of the interesting parameters, right? So later we'll see complexity classes for the circuit computation model. Just like we studied time and space in the Turing machine model, some of the interesting parameters to measure are size, of the circuit. Size of the circuits are just the number of logic gates that are used in the circuits. The number of wires of the circuit, so number of wires, you'll see what they are when we with some examples. And fan-in, again, fan-in means what is the maximum number of inputs any gate can take. Okay, this is what is called fan-in. Again, size and fan-in you may have heard when you study digital logic in your undergraduate, right? So let's try to understand, let's try to realize this function threshold 2 using some circuits, right? So the first approach is what is the brute force approach, right? So we are saying that out of the n bits input, there is at least there are at least 2 ones, right? So why not have a very simple idea? Try all possible pairs of input bits. So like here I have drawn it for 4-bit input, right? x1, x2, x3, x4, and basically I have there are 4 bits, right? 4 input bits, so n input bits, and I have basically n choose 2 AND gates. So because it's 4, we have 6 AND gates. Basically all possibilities, x1, x2, x1, x3, x1, x4, then x2, x3, x2, x4, and x3, x4. 6 possibilities with the 4 inputs. So in general, it is n choose 2 AND gates. Okay, maybe this is not very visible. I'll write with another color. N choose 2 AND gates, right? And if there are 2 ones in the input, at least one of these AND gates will give us a 1, right? If there are 2 ones in the input, xi and xj be the input, so there will be an AND gate which takes xi and xj as input, and that will report a 1, right? And so we finally have an OR gate, right? We finally have an OR gate to check if is there any AND gate that is reporting a 1 or that is reporting true, right? So this is, or just a bit more formally, we have the AND gates between each pair is called Gij, right? So which is an AND between xi and xj, and the circuit is just an OR between all the Gijs. So suppose there are 2 inputs, I and j, for which xi and xj, for which xi and xj are both 1, then Gij will fire, meaning Gij will report true, which means the OR gate will also report true, and the stop gate is the output gate, and that will be, we'll try to illustrate the output as well, right? So let us see how many gates we have, right? How many gates do we have? So we have 6 gates here, 6 AND gates and 1 OR gate. So 6 is n choose 2, so we have n choose 2 AND gates, right? N choose 2 AND gates and 1 OR gate, which is, so n choose 2 is like n into n minus 1 by 2, so it's order n squared. So number of gates is order n squared. Number of wires, so number of wires is just how many wires are there, right? Let's say each input going to one of the gate and each gate going to another, or each output of a gate going to another gate's input, right? So let us see. Each input xi or x1 goes to 3 gates here. That is because x1 is involved in, it has to be compared with each other, right? So, or another way to check is there are n choose 2 gates and each takes 2 input wires. So n choose 2 into 2 is the number of wires to the first level of gates, and above there is an OR gate that takes again 1 input, n choose 1 input from each of these AND gates, so that is n choose 2 wires. So this is the n choose 2 wires are for the inputs to the OR gate. So 2 times n choose 2 for the AND gate and n choose 2 for the OR gate. So total is 3 times n choose 2, even that is asymptotically order n squared. So both number of gates as well as number of wires is order n squared. And fan-in is the maximum number of inputs that any gate has. So, so here all the AND gates take fan in 2, but the OR gate has fan in n choose 2, right? So the AND gates have fan in 2, but the OR gates have n choose 2, and n choose 2 is what we call unbounded, meaning the number of inputs or the fan in for that gate is actually dependent on the input itself, meaning that if n is bigger, then the fan in also will be bigger. But the AND gates, it's always 2, so it is fixed, whereas the OR gate, it is unbounded. When the input increases, the number of inputs to the OR gate increases. So that is what we call unbounded fan in. And in circuits, right, so as you may have imagined already, it is desirable to bring down each of these parameters, right? Gates, wires, fan in. It's better to have smaller of each of these, right? These are all resources, and we want to be economical in using them, right? So we saw the brute force approach, which uses order n squared gates, n squared wires, and unbounded fan in. Now let's consider another approach called, which we'll call the recursive approach, right? So what is the recursive approach? So if there are two, again, if there are, so we want to check whether there are two input bits xi and xj which are both 1. So now consider right, so x1, x2, etc. xn divided by 2, and then xn divided by 2 plus 1 up to xn. So there are 3 possibilities. Either there are 2 ones in the first half, x1 to xn by 2, or there are 2 ones in the second half, xn by 2 plus 1 to xn, or each half has only 1 but then each half separately has 1 right? So there are 3 possibilities by which you could have 2 ones. So if the first half has a 1, we could use a recursive formula. So that's what we are trying to implement here. So in the left half, right, we are trying to implement, if basically we are using the same circuit, a smaller instance of the same circuit. We are using a threshold realization which takes n by 2 bits, right? And similarly in the right side, we are again using a threshold realization which takes n by 2 bits. However, there is a third possibility, that is, there is 1 1 on the left side and 1 1 on the right side. So in order to realize that, we have to basically check, is there a 1 in the left side and if there is a 1 in the right side, and if both of them are there, then we can say okay. So we have an OR gate here, and we have an OR gate here. Basically, this OR gate will fire if the one on the left side, this will fire if there is at least 1 1 on the left side, and this OR gate, the right side one, will fire if there is at least 1 1 on the right side. And if both of them fire, we are okay, right? So we just want to check if both of them will fire, meaning there is 1 1 on the left and 1 1 on the right. So this can go as input to the top level OR gate. So there is a recursive implementation for threshold over n by 2 bits on the left and the right, and then there is this red part which is the verification of whether there is 1 1 on the left and 1 1 on the right. And at the end, we are just taking an OR gate, and this is the output, right? So this is the basic idea. And what is this number of gates here? So just like you might have done recursion or recurrence relations in your undergraduate algorithms, now we need to see, so how many gates do we have? We have one top level gate, this one, and we have 3 gates over here, the red part, so that is 4 gates. But then we have these 2 recursive components. This is basically the threshold function itself implemented recursively. So again, we will have similar structure in the threshold part, right? So basically the size is 2 2 times the size of n by 2, right? So this is threshold function for an n by 2 sized input. So 2 times the size of n by 2 plus the 4 gates that I marked. Right? So I'm erasing this plus the 4 gates that I marked. So 2 times size n by 2 plus 4, and this is something that you may have solved in an undergraduate using the standard Master's recurrence theorem, and this turns out to be linear, right? So this is linear order n if you solve this recurrence. So this is not very difficult to see, you can just try solving it yourself. This may also help you brush up how to solve recurrence relations. The number of wires, okay, so there are n by 2 wires going into the left threshold, there are n by 2 wires going into the right threshold, there are n by 2 going into this OR gate, in the left OR gate, there are n by 2 going into the right OR gate. So n divided by 2 times 4, so that leads to 2n wires over here. Then there are 5 wires, so which I will mark with green. There is 1, there is 2, there is 3, there is 4, there is 5. There are 5 wires extra. So 2n plus 5. And then there are whatever wires are there inside each of these threshold n by 2 gates. Right? So 2 times wires of n by 2, which is basically the recursive call. And if you work that out, you will get order n log n. In fact, if you work this out, you may get n log n, but there may be a bit of overcounting here, because you may be counting the same wire that is going out of this x1 x2 inside as well, but still I think you will get order n log n. Again, this is something that is standard recurrence solving, that you can work it out. So now from n squared and n squared gates and wires, so this one is the number of gates is size, right? N squared and n squared. Now we have n and n log n, right? And the first one had unbounded fan-in, whereas this one also seems to have unbounded fan-in. But there may be a way to reduce the unbounded fan-in. So for instance, this red OR gate, right, the one that I have circled, that takes n by 2 fan-in, right? Whereas the other gate, the top level OR gate, takes 3, then the AND gate takes 2. But however, notice that inside these threshold functions, inside the recursive calls, you will have other OR gates which you may be able to combine to get the OR gate over here. So you may not have to actually implement an OR gate with n by 2 fan-in or at the top level. So what I'm saying is, if you expand this threshold n by 2 gate, right, you will again find one OR gate that takes n by 2 plus 1 to 3n by 4. So I'm expanding the right side threshold gate, and then another OR gate which has 3n divided by 4 plus 1 to xn. Okay, so I've omitted the superscripts. Right, so it's xn by 2 plus 1 to x3n by 4 and x3n by 4 plus 1 to xn, and this would already be implemented in this threshold gate. So all you need to do outside for the OR from xn divided by 2 plus 1 to xn is to just take the OR of these two, right? So OR of these two, right? So you could just bring it out and take another OR, right? This is something that you can do. I'll just erase this part, and so you may not need an unbounded fan-in, right? So I'll just leave a question mark. So it is not really unbounded fan-in. If you want, you can implement it with a bounded fan-in. Bounded fan-in meaning fan-in 2 or 3 or something like that. It will not vary based on the input. Okay. The third approach that I want to consider is what I will call the hiding approach. Okay. Again, all of these are interesting and it's clever in their own ways, right? So we have two approaches seen already. One where size and wires were both n squared. The second where size was n and the wires was n log n. The second we said had bounded fan-in. Third one is what is called hiding approach. So again the question is this, are there two xi's which are both 1, xi equal to 1, xj equal to 1, right, where I not equal to j. So if there are two such xi's which are both 1s, then even if we hide one of the xi's and take an OR of the remaining bits, it should still give us 1, because there are at least two 1s. So even if you hide any input bit, the OR of the remaining things should give us a 1. And this will happen only when there are two input bits equal to 1. If there is only one input bit equal to 1, then if you hide that, the rest of them will not give an 1 upon ORing them. So what we do in this approach is to simply take all the possible there are n input bits. So you hide x1 first, then you hide x2 first, then you hide x3 first, x3, and so on till finally you hide xn. And for all of this, once you hide x1, you take the OR with the remaining bits. Then you hide x2, you take the OR with the remaining bits, and so on. And then finally you check whether all of these are 1. If all of these are 1, this means that there are two 1s in the input. Okay, so you have ORs at the bottom level and then an AND at the top level. So first I have, so maybe I'll just write the x1 here, which I have hidden, then x2 I have hidden, and then x3 I have hidden, and finally xn is being hidden, right? So x1, x2, xn, so this smudging indicates it being hidden. Right? And we are taking an OR of all the input bits except, so I'm looking at this one, we are taking OR of all input bits except x1 in the first part. And similarly we are taking OR of all input bits except x2 in the second part, and so on till the OR of all bits except xn in the last part, right? And what we really want to know, what we really want to do after this is to take an AND of all the ORs. So we have an AND of all the ORs. Okay, so right, so this is the output. So what is the size here? The size here is I have written n here, which is not quite correct. So there are, okay, there are so how many x1 can be hidden, then x2 can be hidden, then x3 can be hidden. So there are n OR gates at the bottom and plus 1 AND gate. So it's actually n plus 1. Right? The number of sizes is the number of gates. There are n OR gates and 1 AND gate. And the number of wires, again this is not very difficult to see. Each of the OR gates has n minus 1 inputs. So n times n minus 1. Plus the AND gate has n inputs. So that is n plus n. So n times n minus 1 plus n, which is n squared. So size is n plus 1 and fan wires is n squared. The fan-in is unbounded, however, because both OR gate and AND gate take n minus 1 or n inputs, which obviously varies with the input size. So fan is unbounded. Again, this is, so we saw the recursive approach, which took order n size and order n log n number of wires. This one takes linear size and n squared wires, quadratic number of wires. So again, this is not that great, but it's a simpler construction. Okay, so I believe I have 3 more approaches, which I think I will cover in the next lecture. So just to summarize this lecture, I introduced what is the circuit model of computation, right, and the motivations explained. Then explained what is the threshold function, threshold k function, and what we will see we saw in this lecture was threshold 2 function. And we saw three approaches: the brute force approach, the recursive approach, and the hiding approach. And we saw the size, number of wires, and the fan-in of each of these approaches. And just to reiterate, these the parameters like size, wires, fan-in are standard measures of measuring the circuit complexity. So just like we saw time, space, etc. in the case of Turing machine model, these are the parameters that are considered for the circuit complexity model.
Swayam Prabha, Digital India, Educated India.
Hello and welcome to lecture 34 of the course Computational Complexity. In the last lecture, we saw the threshold 2 function, which requires two of the input bits to be 1. Right? We saw three approaches using circuits on how to decide that. Now we are going to see another three approaches to decide the threshold 2 function in this lecture. Okay. So in the previous lecture we saw brute force approach, hiding approach, and the recursive approach. So the approach that we will see first is the partition approach. Okay. So again, the key thing is that there has to be two ones in the input. So in the recursive approach, right, we divide it into two halves, x1 to xn by 2 and xn by 2 plus 1 to xn. Now another way of doing that could be to and then did this recursive thing. Another way is to try all the possible partitions. So one way is to x1 and x1 on one side and everything else on the other side, x1 x2 on one side and x3 x4 up to others, rest on the other side, x1 x2 x3 on one side, and so on. So we can consider partitions like this, where we consider up to a certain I, right? So in general situation it is this: x1 to xi on one side and xi to xi plus 1 to xn on the other side. So there are n minus 1 possible such partitions that we can consider: x1 on one side, x1 x2 on one side, x1 x2 x3, and so on up to x1 x2 x3 up to xi on one side, right? This is the general case. So there are n minus 1 such partitions we can consider. If this is a yes instance of the threshold function, meaning there are two values, xi and xj, for which both the bits xi and xj are 1. That means that for at least one of these parts, right, at least one of these partitions, both sides should have at least 1 1, right? So just to illustrate this, suppose this is the x1, x2 and so on, right, x3, right? Suppose, let's say this is one, there are only two bits which are 1. Let's say this is x7 and let's say this is x13, right? So now consider any partition that breaks it between that. So now the left half has x7 and the right half has x13, right? So basically if xi and xj are the two bits that are 1, then consider let's say without loss of generality xj is bigger than I. Now consider the ith partition, which takes xi onto one side, and naturally since j is bigger than I, j will be on the other side. So this partition, the ith partition, will split the two ones into two halves. Then all that we need to check is there a 1 in both the halves? Is there at least 1 in both the halves or both the parts? These are not really halves. So this is the partition approach. And let's try how to formalize this. So again, I have said the basic idea, which is to check whether there's a partition, whether there's a 1 in the left and 1 in the right. So we do this. Again, this top one is the output, right? So we try all possible partitions, x1 on one side and x2 to xn on the other side, x1, x2 on one side and x3 to xn on the other side, and so on up to x1, x2 up to xn minus 1 on one side and xn on the other side. And then in each of these partitions, we take the OR of each part. So here x1 is alone, so there is no OR in the first part. x2 to xn is one part, so we have this OR gate, right? In the second, x1, x2 form an OR gate, x3 to xn form an OR gate. In the last, x1 to xn minus 1 forms an OR gate, and obviously xn is alone, so there is no need of an OR gate, right? And then for each of these partitions, we have ANDs. So the ANDs are in this level, right? Basically, we need to check, we need to have a 1 in this half and a 1 in this part, right? So we need to have an AND gate, and at the top we have an OR gate, right? So I suppose the correctness is evident from what I have described above this or before this. So size, how many gates are there? There are n minus 1 possible partitions, right? And for each of these, so this is one partition, this is one partition, this is one partition, right? For each of these partitions, in general, we have 3 gates, 2 OR and 1 AND. So that's why it is 3 times n minus 1, right? But and plus one top level gate, which is the output gate. So 3 times n minus 1 plus the output gate, 3 times n minus 1 plus 1. And I have subtracted 2 here, this minus 2. It is because the leftmost partition and the rightmost partition have 1 gate less. They just need 2 gates, 1 OR and 1 AND, because they have 1 singleton part each. So but anyway, this minus 2 doesn't really change the asymptotic factor. It's still order n, right? It's 3n minus 1 plus 1 minus 2. It's still order n, which is what we are bothered about. And number of wires. So at the bottom level itself, x1 goes to each partition requires n wires, each partition, and there are n minus 1 partitions. So n times n minus 1 many wires are required in the bottom level itself to the OR gates. Then to AND gates, there are n minus 1 partitions, and there are 2 wires per part, so 2 times n minus 1. And then at the top level, again n minus 1 partitions go into an OR gate, so that is n minus 1 wires. So n times n minus 1 plus 2 times n minus 1 plus n minus 1. Again, I put less than or equal to here because the extreme left and right parts may have slightly less. But the key thing is this n times n minus 1, which contributes to an order n squared, right? So asymptotically it's order n squared. And fan-in is unbounded because consider all these, that either the top level gate or the bottom gates, all the OR gates have take n input or n minus 1 inputs, right? So the fan-in is unbounded. So size is linear, wires is quadratic, and fan-in is unbounded. So we saw many approaches already, and so far this the recursive approach seems to be the best, right? Size is order n, wires is order n log n, and fan-in is unbounded on the first appearance, but it seems like it can be made bounded. Okay, moving on. The next one is a recursive grid-based approach. Okay, again, this one needs to first assume that n is a perfect square for this to visualize this. If n is not a perfect square, we can always pad a bunch of inputs. You can go to the next square and then execute this, right? So suppose n is 500 is not a perfect square, then you can go to 529, which is the next perfect square, right? So add some few extra bits which we control and make it 0, because make it false, because we need to see if there are 2 bits which are 1 in the first part itself, right? Again, what are we trying to do here? if there are two bits, two positions xi and xj which are both 1, right? Now, either these xi and xj are in different rows, right, which means they are in different rows, or they are in the different columns. They cannot be in the same row and the same column. Same row, same column means they will be at the same position, right? Same position means I is fixed or j is fixed. So either they have to be in two rows or they have to be in two columns. So either two rows, either xi, xj in distinct rows or distinct columns. In distinct columns. Right? And this is what we will formalize in this approach. So either they are in distinct rows or distinct columns. So suppose they are in distinct columns, right? So let us say suppose they are in distinct columns, let's say. That means if you take an OR of all the columns, there will be at least two columns in which there is a 1. So at least two of these column inputs will be true. And then we have a threshold threshold 2 gate or threshold 2 circuit at the with square root n inputs, right? Threshold 2 circuit with square root n inputs to decide that. So this is also potentially a recursive approach. And to check whether there are two ones in distinct rows, again we take OR of all the rows, and if there are two ones in two distinct rows, these ORs, there will be two ORs which will be true. And then we have a threshold, sorry, this is not threshold n, it's threshold 2 with square root n inputs. Threshold 2 circuit with square root n inputs, and either you want the rows, the row threshold to be true or the column threshold to be true. So you take an OR of both of them, and this is the output, right? So hopefully the correctness is evident, right? Either there are two rows in which xi and xj are 1 or two columns. So if there are two rows, then this threshold function will fire, the one that corresponds to the rows. If there are two distinct columns, this green underlined threshold function, the one corresponding to the columns, will fire. And finally we have an OR. So let's see the size, wires, etc. Right? Again, I have written the idea here. If x is equal to x is in the threshold, then xi equal to xj is 1, where I and j are distinct. So either they are different rows or different columns. So size, how many gates? We have 1, 2, 3 up to square root n gates here. Square root n gates corresponding to columns, right? Square root n gates corresponding to the rows, and one OR gate. So 2 times square root n plus 1 plus whatever is the recursive component, that is 2 times size of square root n, because this is threshold 2 gates of size square root n, right? So this is the size. One thing that we can try, in fact you can try that as an exercise, is to now compute this recursion, right? So this is size n equal to 2 times size square root n plus 2 times square root n plus 1. So this recursion can be computed. This is not, the master theorem is not immediately applicable here because it is not of that form. We have n going to square root n, but there are some transformation tricks that you can employ and solve this. I'm not going to get into that because this is not a master theorem or discrete math or algorithms course, but you can work it out. However, to get a decent solution, we do not need a recursive approach. So for instance, this threshold 2 with square root n input need not be implemented in the same recursive manner. You don't need the same kind of grid based approach here. We could use the brute force approach, for instance. So recall, the brute force approach had size n squared and and wires also n squared. So, but that is when there are n bit input. So when the inputs are square root n bits, then the brute force approach will give us a size n, order n approach, right? So which is what I have written here. If we can use the brute force approach to implement the threshold function on square root n input bits, that will take, so that will make size square root n to be order n, and overall this function will also be order n, right? So this will be order n. Sorry, I'll not use, the green is not so nice to write. It's good to highlight because I made it thick. The size of this circuit will be order n. Wires, you can see that x1, there are two wires going from x1, one to the row based OR gate, right, and one going to the, so I'll circle that, this OR gate, sorry, this OR gate, x1 to this OR gate and x1 to this OR gate. And likewise for any xi, there are two outgoing wires. So that is 2 times, so there are n inputs, so there are 2 times n wires plus square root n wires going to each of the threshold function on square root n inputs. So 2n I already explained, 2 times square root n for each of the threshold going into the threshold function on square root n inputs, and then 2 wires going into the OR gate. So this is explained. What remains is the number of wires inside the threshold square root n realization or the construction, and that I am just calling it 2 times wires of square root n. Again, one thing that we can do is to compute this in a recursive setting. So you could implement it recursively where each threshold square root n the threshold square root n itself is realized using a similar grid based approach. So again, it will be a recursive calculation. As I said before, the Master's theorem does not lend nicely to this, but you can solve it with some simple tricks. But however, just like in the case of size, you don't need to do that, because even if you use the brute force approach to realize the threshold 2 function on square root n inputs, even then the number of wires will be linear or order n, because it is on square root n input, so square of that will be order n. So overall you will get this also order n, even if you use the brute force approach for implementing the threshold 2 circuit on square root n inputs. You don't need a recursive approach, but you can calculate what happens when you try the recursive approach, right? And fan-in, again you can check each of these OR gates, right? It takes fan-in square root n, which varies with the input, which is not a constant, right? So it is unbounded fan-in. So I'll just write that fan-in, and as an exercise you can work out the recursions. Okay, so this is the grid recursive approach with the grid, but again it need not be recursive. And finally, number 6 is binary partitions. Again, the idea is same here. We already mentioned this idea in the partition approach, that if there are 2 bits which are both 1, then there has to be some part, some partitioning where each part has a 1. So we are just trying out, so basically most of these approaches we are trying out different ways to separate these ones into 2 parts, so that, and checking whether each part has a 1, right? So binary partitions is a similar approach. So suppose xi and xj are the 2 bit positions which are both 1. Now you can consider the binary representation of xi and xj. So for simplicity, let's take x7 and x12. Now x7 is nothing but 0 1 1 1, x12 is 1 1 0 0. So there are positions where they differ, and any two numbers there will be some position where they differ. They cannot have the same binary representation if they are two different numbers, right? So here is one position where they differ, let's say this position. So now there will be some k in which I and j differ in the kth position, where the kth bitwise position, right? So now we will consider the following partitions. Right? Maybe I will explain the partitions in terms of 3-bit numbers. One is where for each k, where k is a bit position, we are trying to categorize into two separate parts. So one is when k is the least significant bit. So when you have 3-bit inputs, when k is the least significant bit, k equal to 0 means the least LSB is 0, which means that we are just dealing with even numbers. When k equal to 1, we are just, the least significant bit is 1, which means we are dealing with odd numbers. So the partitions are so 1 1 0 0 0 0. So maybe I don't need to write this down, but similarly you can consider the partitions where the middle bit differs and the partitions where the most significant bit differs. So the partition where the most significant bit differs will be 0 1 2 3 will be in one part, 4 5 6 7 will be in the other part, right? And partition where the middle bit differs will be, I think 0 1 will be in one part, 0 1 5 and 4 and 5 will be in one part, 2 3 6 and 7 will be in the other part. So these are the three partitions, one for each bit position, that we get for 3-bit numbers. Okay, so there are three ways to partition 3-bit numbers. Perhaps I'll just write it down anyway, right? So the first part is 0 0 0 0 1 0 1 1 0 1 0 0. This is on one side, and 0 0 1 1 1 1 0 1 1 and 1 0 1. This is first partition. Second partition is 0 0 0 0 0 1 0 1 1 0 1 0 1 0 0 1 0 1 1 1 1 1 1 0, and finally based on the middle bit 0 0 0 0 0 1 1 0 0 and 1 0 1, right? And finally 0 1 0 0 1 1 1 1 0 1 1 1, right? So there are three ways to partition the 3-bit numbers, and if for k for 4-bit numbers you will have 4 ways to do this, right? So now consider the following partitions for the 3-bit numbers, or for k bit. For when you are dealing with numbers 1 to n, there will be log n partitions, right? Because to represent n bit number, to represent n, we require log n bits, right? Okay, so we'll have log n such partitions, right? So in this case n is 8 because you have inputs ranging from 0 to 7. There are 8-bit inputs, right? 8 positions, and but it can be realized using 3 bits. Okay, so now what we do is, if I and j are xi and xj are both 1, there is some partition where I and j differ, or some bit position where I and j differ, and now consider that partition, right? There has to be a 1 in this part as well as this part. So both parts have to have a 1. So you take an or here, and an AND of both of them, right? So fk is taking an or in the 0 part and or in the 1 part at the kth position. So bk0 is the set of all I which has 0 in the kth position. bk1 is the set of all j which has 1 in the kth position, and then take an OR of both and then an AND of them together. So Fk will be 1 if and only if there is an I in one of the parts and there is a j in the other part. And finally, we are just checking, is there any partitioning such that there is I in one part, there is a 1 in each part. So basically, we need an OR of all the Fk, which is what we do here, right? So whatever k is where I and j differ, for that k, Fk will be equal to 1. Again, the correctness, I think I have explained it good enough. And what remains is to compute the size, wires and fan-in. Let's compute the size. Let's see. So to compute Fk, how many gates are there? So 1, 2, 3. There is an OR gate for the one half, OR gate for the other half, and an AND gate. So computing Fk requires 3, but multiplied by number of Fks. So how many Ks are there? Ks, how many bit positions we need, which is log n. So 3 times log n plus an OR gate at the top level, which is to compute F. So 3 log n plus 1. And this is the first time we are seeing a sublinear sized circuit. Right? Previous everything we saw order n squared, order n, I think even order n log n, I think. Right? So this is order n, this is order n, this is n, right? This is n, okay, n squared. In fact, we didn't see n log n, we saw n and n squared. Wires. So wires, if you see, each xi contributes to, or each xi needs to give input to each part for each k, right? It may be the 0 part or 1 part, but for each k it needs to give input to one of the parts. So that will give us n times log n, because each xi will give one input to one k. So there are n xi's and there are k log n many k's. So n times log n, right? And then the number of wires. So this to the AND gate that computes Fk, we need 2 wires, right? So which is again 2 times log n plus again log n wires to compute F. But anyway, log n is kind of dominated by this n log n term here. So this is again, or rather this is order n log n. And finally fan-in, this should not be that difficult. Even the bottom level or the top level F compute requires log n many inputs. So log n itself is variable with n, so it is not fixed. So this is unbounded. So here we have a sublinear sized circuit, but the number of wires goes up to order n log n. Yeah, with that, I think we are at the end of this lecture. So we saw 3 more realizations of the threshold 2 function on n bits, and the binary partitions, the recursive grid based approach, and the partition based approach. And we saw how each realization does some kind of a trade-off. Some parameters go up while some parameters go down. So there is a kind of balancing that we need to do in each of these cases. There are also other parameters that are of interest in the case of circuits, like depth is another parameter. In any case, we will hope this gives you an idea of what circuits are and how to compute. You may also have noted how, like, for a certain number of inputs, like one circuit construction only fits a certain specific input length. If I make a circuit for an n length input, I can only feed n length inputs. I cannot use it to feed n plus 1 or n plus like 2n sized inputs. So this is what I meant when I said non-uniform. Like I could potentially have the circuit for size n of a certain type and circuit for n+1 input bits be of a different type. So I could have a non-uniform approach in having different circuits for different input lengths, right? For more details, I think, and the formal definition of circuits, I gave a very high level definition. We will take it up in the next week, where we will see formal definition of the circuits and also see some basic results, like which functions have circuits, how much size do those circuits take, do all functions, do they have circuit realizations, etc. Right? For instance, in the case of Turing machines, there are languages which are undecidable. But what about circuits? Are there undecidable or circuits, languages that do not have circuits? Right? So we'll see all of that in the next week. With that, we close week 6. Thank you.
Swayam Prabha. Digital India. Educated India.
बाबू मोशाई, जिंदगी लंबी नहीं बड़ी होनी चाहिए. This is a dialogue from one of my favorite Hindi movies, Anand. You must be wondering what I'm talking. Well, this is what our next joy is all about. Movies.
I'm going to tell you all a nice new game. The game is called Guess the Movie Name. Right? So the game is very simple. I will try to write a movie name like this. Okay? There is this movie with 1, 2, 3, 4, 5, 6, 7 letters. Can you guess the name of the movie? Obviously, there are going to be a lot of movies with 7 letters. So I'll give you a hint. It's a Hollywood movie and a very popular one.